Okay, record on this computer. Okay. Okay, we will continue from our last time. I think last time we end up with the mean effective pressures. Okay, and we already give you the conventional number, right? If you want to design an engine, right, then you can use this conventional number, right, as your starting point to do your engine design. The good thing about using of these conventional design numbers is the good thing is that if you go by this number, right, and when you want to manufacture the engines, you can go to the factories, right? The result of your design that based on conventional number, right, it will make you a little bit easy, right, in order to when you go to the manufacturing people and ask them to do the thing that you design on your paper, right? Because since you go with conventionals, they are also conventionals, right? So for example, you use this number to design your engine, you come up with the cylinder, you come up with the sizings of your cylinder, you come up with the sizing of your piston, your connecting rod and everything, right? So what you design, right, is something that they already be able to produce, right? The thickness is conventional, the sizing is conventional, right? The length of the connecting rod come up in the conventional length or within the length that they used to produce, right? So that make it easy if you go by conventionals. That's the reason why I give you all of this number, right? For the mean effective pressure, it's just not the number that you just look through, right? But you can use this number for your design, right? And that means that I come up with the examples, which is a design example that you can go back to all the numbers that I mentioned to you. It's not only the mean effective pressure, also the compression ratios, right? And also all the ratios, right? When we're talking about the engine geometry, right? We come up with the conventional ratio, several of that. Okay, so you can go back and use that number for your engine design. But if you don't want to use all that conventional numbers, right, then you have to do a lot of research when you go for manufacturing, because the factory said they never used to produce such a big cylinder like this with this kind of thickness, right? They never manufacture thing like this. Okay, so you have to go to do some research, right, in order to come up with something or some process that factory can do the thing that you design for you. Okay, so this is the examples, the design examples, right? We have a 4-cylinder automotive spark ignition engine that is being designed to provide a maximum brake torque of 150 Newton meters, right? So this is the requirement, give you a maximum brake torque, right? And this brake torque maximum one have to happen in the mid-speed length, right? Mid-speed length, which is about 3,000 revolution per minute. So this is just a requirement they give to the designers, right? So what the designer have to do, right? They have to find out what is the engine geometry, right? So they have to estimate the required engine displacement, which is the displacement volume of the engine, right? The bore of the cylinders, right? The piston bore also, and the stroke, right? And with the maximum torque and with this engine geometry, what is the maximum power that this engine will deliver, right? So you can see that they only give you one information, right? The maximum brake torque at 3000 RPM. The rest is up to you, right? How you gonna design your engine in order to that your engine can deliver this 150 Newton meter at 3000 revolution per minute. So what are we going to do? Right? We learned about the BMEP already, right? So we have to make an assumption, or we have to assume the value of the BMEP, right? So how we can come up with the number? Then you might have to go back to what we used to say before, right? Okay, if we want this engine to be a naturally aspirated engine, right? They already give us it have to be a spark ignition engine. And then if we want to design this engine to be a naturally aspirated, right? The maximum BMEP that we can use for the maximum torque, right? Which is about 3000 RPM here, the conventional one, right? You can come up with the number that within this length, right? That within this length, 850 to 1050. Okay, so let's choose what 925. Right? You go for 925 kPa for the brake mean effective pressure. So we will use this brake mean effective pressure to come up with the displacement volume, right? Because we know the formula, right? We have this formula. The BMEP down here and above here is 6.28 times the number of crank revolutions times with the maximum torque, right? Because they give us the maximum torque. So we can come up with the total displacement volume, right? Which is about what? If you put in the correct unit, then you get the correct answer, right? The correct answer is 2 decimeter, cubic decimeter, right? So this is the displacement volume, right, of this engine based on 925 kPa for the brake mean effective pressures, right? And from this volume, right, you want to come up with the bore and the stroke, right? You can go by these equations in which we have what? They say 4 cylinder. So this is the total volume. So we have to time 4 here, right? Because this expression is for each cylinder, right? So with this now, another thing is, what is the ratio between the bore to the stroke, right? Because we have 2 unknown here, the bore and the stroke. So how we come up? Oh, stop again. Have to stop the chairs. Okay, so how to come up with the bore and the stroke, right? We have to make another assumptions, right? How? Go back to what number that we have, right? For small and the medium size spark ignition engine, the bore to stroke is about what? 0.8 to 1.2, right? So we can choose any number of this ratio, right? As long as that number is within this length, okay? So let's say what they choose? They choose bore equal to the stroke, right? So when bore equal to stroke, we have a special name for this engine. They call it a square engine, okay? Bore equals stroke. So when bore equals stroke, we can easily solve these equations, right, in order to come up with the number for bore and the number for the stroke here. Okay, so we have bore and stroke equal to 86 millimeter, right? How about the number what? How about the number the revolutions, right? They want to come up with the revolution. So the maximum speed, the maximum rated engine speed, right? This is the maximum rated engine speed. Okay, how we can determine it? Right? This is what we want our engine to go, right? This is the maximum one that our engine can go. So it depends on what? It depends on the maximum mean piston speed, right? Because we have this equation, right? The average mean piston speed is equal to 2 times the stroke times the number of revolutions or the speed of the engines, right? Okay, so if we want to find the maximum speed, right, maximum engine speed here, right? So we have to assume again, right, for this maximum mean piston speed. So, and what number that we should go? We have this table, right? This table, they said we have what the car SI engine, right, with the maximum speed about 7,500. This is the maximum speed, right? And the maximum mean piston speed is about what? 25, because this is maximum 1, so this is the maximum mean piston speed 20. Okay, so we can choose 20 or below this if we want our speed not to go up higher than this 7,500 RPM, right? So in here they choose 15 meter per second. Okay, you can choose 20 and then you will check that your maximum speed is go higher than 7,500 RPM or not. Understand? Okay, because when you look at the table, there are two numbers that are in your consideration. 7,500 RPM, this is the maximum. Okay, and this is the mean piston speed, right? About approximately about 20 meter per second. Okay, so in here they decide to choose 15 meter per second with the stroke equal to 86 millimeter. So they put it into this equation. What they come up is what? The maximum speed is about 87 revolution per second, right? Which is about 5,200 revolution per minute, right? So it's below 7,500 RPM. So if you satisfy with this, then you can stop your calculation here, that you prefer to go for the maximum engine speed at 5,200 RPM. Right? It depends on your design. Then we want to calculate the maximum powers, right? The maximum power. These maximum powers, right, have to be estimated from what? From the typical BMEP value at the maximum power. So again, we have to assume, right, what should be our BMEP, right, when the maximum brake power occurs. So how we can assume? Go back to our data, right? We use the naturally aspirated SI engine. We use the maximum BMEP at the maximum torque already. So how about at maximum rated powers? At maximum rated power, the BMEP will reduce to about what? 10 to 15% lower, right, than the number here. So what we choose in this example is 800 kPa, right? 800 kPa, right, is lower than this 550, right, in about 10 to 15% lower, right? So we choose 800 kPa, right, to be our brake mean effective pressures when the maximum brake power occurs. So with this BMEP, right, we can calculate the maximum brake powers, right, because we know the displacement volume, we know the maximum engine speed, right, we know our crank revolutions, number of crank revolutions, right here. So the brake mean, the brake power, the maximum brake power for our design now is 70 kilowatt, 70 kilowatt. Right? So this is the example, the design example, in which you can see that user only give us requirements. Right? In here, they give us maximum torque at what RPM. Right? This is the only information. So the rest is depend on your design. Right? The rest is depend on your design. And in this design, we go for conventional design. Right? We want, because we want to produce this engine, right? when we go to the factory can produce this engine for us, right? So we go for conventional design. We do not go for creative design. Design not necessary to be creative all the time, because if you creative too much, right, it can be only on the papers, right? You send this paper to your design paper to the factory said, I cannot build it because I have no experience. I never used to, right? I never make this kind of thing, right? I make this thing, but not this size, right? I never make this big size, right? So I don't want to take the job, okay? So design can be conventional, design can be creative, right? And in here, it's a conventional design, right? By conventional design, you have to go back to the data that are available for you, right? That I already showed, right? Yeah, everything is the data that is available to you for you to design your engines. Okay. Okay. So the next parameters, right, for the engine performance is the specific fuel consumptions and the efficiency, right? Specific fuel consumption and efficiency, right? The term of specific consumption can be determined from here, right? It is the fuel mass flow rate divided by the power output. That means what? The SFC will tell us that if I want to have 1 unit of the output powers, how much that I have to use my fuel, right? And based on how much that I have to use my fuel, right, it's gonna refer also to how much money that I have to pay for, right? Because you have to buy the fuel here, right? So SFC is one parameter that we can use to compare the performance of the engines, like this, okay? And for the SFC, I show you here, right, in 2 units, right? If you want your SFC to come up with microgram per joule, right? So your mass, the fuel mass flow rate, right, have to be gram per seconds, and the power have to be in kilowatt, right? And if you want your AFC to go with gram per kilowatt hours, right, then your fuel mass flow rate have to be gram per hour, right? It's the bigger number than this one, right? Because this is gram per second, this is gram per hour, right? And divided by the power, which is kilowatt, right? This power is the output power or the power output, okay? Always, okay? So, or not always, change it, because sometimes if we say power output, this SFC will become BSFC, the brake specific fuel consumption, right? If it divided by the brake power, which is the power output, right? And if it divided by indicated power, right, then it's gonna be indicated SFC with the letter I in front of SFC. Okay. Okay, the typical number of the brake specific fuel consumption for the SI engine is about 75 microgram per joule. Right? That means what? I give you one number. It means when you design your engine, you should not have the brake specific fuel consumption higher than this, because that's gonna be what? Bad design. Okay. If I give you one number, right, that means you have to try to design your engine lower than this number. Okay, if you go over, it's a bad design. Okay, so for SI engine, right, the typical number for the brake specific fuel consumption is about 75 microgram per joule or 270 gram per kilowatt hour. For large compressed ignition engine, right, the BSFC is usually below than 55 microgram per joule or below 198 gram per kilowatt. So this is the number, the typical number for the BSFC, right, for both the SI and the CI engine. Okay. Now, if I make a plot of the BSFC, the brake specific fuel consumption, and the engine speed, for the different compression ratio, right? For example, in here we have the compression ratio equal to 10 and compression ratio equal to 8, right? You see the change of your brake specific fuel consumptions throughout the length of your engine speed, right? One thing that you can find out from this graph is that if you design your engine for a higher compression ratio, right, you can expect that you will have a lower BSFC, right, than the higher compression ratio, than the lower compression ratio, right? So for lower compression ratio, you have higher brake specific consumptions, right? So if you go for higher compression ratio, you will have a lower brake specific consumption. And another thing that you can observe is that you will get the minimum of the BSFC, right, near the mid-length of your engines. The minimum one, right, is not at the beginning, not at the end, right? It's near the mid-length of your engine, which is somewhere between 3,000 to 4,000 RPM. Okay, so this information is also for you to test your engine, right? When you design your engine, right, you build it, you run it, right? All of these numbers are the checking number for your engine. Okay, another parameter is called the fuel conversion efficiency, right? Here we call it fuel conversion efficiency, but in thermodynamics, we call it the thermal efficiency, right? So this efficiency is, if you remember, right, is an energy conversion efficiency. It differs from the mechanical efficiency. Mechanical efficiency is not the energy conversion efficiency, right? Because when we talk about mechanical efficiency, we talk about the same energies, right? Which is work versus work, right? Work versus work. One is the work input, another is the work output, right? So it's the same energy that we want to see how it can transfer, right? From the original to the destinations. Okay. But for the fuel conversion efficiency, this is the energy conversion because we compare between two different energies, right? One is the work, right? Because this is always what we want from our engine. Another one is the heat, the input heat, right? In here, our input heat come out from where? The mass of the fuel times with the heating value of the fuel, right? What kind of fuel we use, what is heating value, right? So we have, this is the amount of heat input. Now, if we want to change this term or convert this term into the SFC, right? See, we have this work divided by the fuel, the mass of the fuel, right? Which is what? Which is 1 over SFC here, right? So with SFC and the heating value, we can come up with the fuel conversion efficiency or the thermal efficiency. Okay, here. And again, in here, I give you 2 units of the parameter that can come up with the fuel conversion efficiency, right? We have LFC and the heating value here, right? If our LFC is microgram per joule, our heating value have to be megajoule per kilogram, right? And if we use LFC in terms of gram per kilowatt hour, right? Our heating value is still megajoule per kilogram, but we have to time it with 3,600. Okay, otherwise you probably come up with the SFC, the high, very large amount of the SFC, or too small amount of SFC. If you do not time it with 3,600. Okay. the typical heating value for the hydrocarbon or the fuel that we use, right, is about 42 to 44 megajoule per kilogram. This is the typical value for the heating value. Okay. The next one is the air-fuel ratio or fuel-air ratio. Right? The air-fuel ratio is the air mass flow rate divided by the fuel mass flow rate. Right? For the fuel-air ratio, it goes in another way around. Right? We have the fuel mass flow rate divided by the air mass flow rate. Okay. Now I give you again here the typical of the air-fuel ratio for the SI engine and the typical value for the air-fuel ratio of the CI engine. Right? For the SI engine, the air-fuel ratio is in between 12 to 18. Right? For the CI engine, it's about 18 to 70. Not be surprised, right? 70. That means what? For the CI engine, they can go for what? A very, very lean mixture, right? When we talk about lean mixtures, it means what? The air-fuel ratio is higher than the stoichiometric ratio, and the stoichiometric ratio is 14.7. Right? So with this number, the air-fuel ratio for the CI engine, right? Now you know that for the CI engine, it prefers to have a lean mixtures, right? Not stoichiometric, not what? Not least mixtures, right? But for SI engine, the number lie in between the least mixture, right? The least mixture and the lean mixtures, right? Because it go from 12, which is considered to be rich mixture, and 18, which is lean mixtures. Okay, so SI engine, you can use lean or rich, right? But CI preferably it have to be lean mixtures. Right? And the fuel air ratio is shown right here, right? Because it is 1 over air fuel ratio. Okay. Now, if I make a plot from all the parameter that I just mentioned, right? For example, the power, we mentioned it already, the mean effective pressures, and the NFC, right? If I make the plot of all these parameters for the SI engine at the different engine speed, this is the map that we will have, right? It's called the engine fuel consumption map here, right? In the map, here is the mean pressure, right? Which is the mean effective pressure. Here, sometimes they call it the mean pressure. Okay. Here is the powers, right? Below here is the engine speed. And each line here, right, which is the contour line, we call it a contour line, represent the constant value of each NFC, right? So we have 255, 260, 270, right, for the NFC in the unit of what? Gram per kilowatt hour. Okay, and what is the dotted line here? This is the line of constant powers, right? So it starts from 20, so it means this is a constant 20 kilowatt powers, right? If it starts from 40, it is a constant 40 kilowatt powers. Okay, so what I want to show you here on this map, right, is this, right? For constant powers, right? That means if you run your engine in order to get a constant power, let's say 20 kilowatt, right? You can have many running conditions of your engine, right? For your engine to be able to deliver 20 kilowatt, right? For example, if you run your engine at speed less than 2000, somewhere between 1800, right? And with your engine produce the mean effective pressure about 7, right? You can come up with 20 kilowatt. Right? And if you run your engine at higher speed, let's say about 42, 43,000 or 42, 4300 here, right? and your engine produce about 2.8 something of the mean effective pressure, right? You can also get 20 kilowatt out from your engine. Right? The difference between these two conditions is on the SFC, right? On the SFC, that will tell you how wisely you are to run your engine, right? If you run at the slow speed here with 20 kilowatt, the cost that you have to pay to this engine is only 260 grams of fuel per kilowatt hour, right? Only 260. But if you run 20 kilowatt at 4,000 and more here, right? The cost that you have to pay for your engine will be 400 grams per kilowatt hour, right? So the difference is on the with the same power output. So that's why you have to think of what condition that you want to run your engine. Right? Okay. Apart from the powers, right, they can change from power to torque, right? So we have another fuel consumption map, right, in terms of torque and also for the SFC, right? Torque also the same. In here we have the torque right here, we have the engine speed right here. Also we have a control line for each NFC here, right? And the dark big line here, right, represent the peak torque curve or the maximum torque that the engine can deliver to you at each particular speed here, right? So this is the cap of the torque that the engine can deliver to you. It cannot give you higher torque than this at this particular speed here, right? For each particular speed or each specific speed here. Okay. So for the torque, the same as the powers, right? If you want to get a constant torque, right, you can run engine at many conditions also, right? For example, if you want to have an engine to deliver about 100 Newton meter, you can run your engine at about 2400 or about 3300, right? You still get the same torque from this engine, right? But the difference again, right, is the SFC, right? If you run your engine at lower speed, right, you pay less because this is only 270, while this one is about 290 grams per kilowatt hour, right? So this is how the engine fuel consumption map tells us, right? And by this, right, we can determine how our engine should be run, right? Should be run, right? When it change from one speed to another speed and to another speed, right? We can make a plot. We can make a plot like this red color line here. I start from here, okay? Right? Because in here we still don't use any torque, but in here we start to use torque. So this is the part for our engine to run, right? And this, if we make this part such that the engine can go for maximum efficiency every time that it change the speed, then this will be the maximum efficiency line for our engine to operate, right? So in terms of maximum efficiency, it means every time that it change its speed and deliver different torque, right, we will be sure that we pay the minimum all the time. We pay the minimum amount of the fuel all the time, right? Because this is the maximum efficiency line, right? All of the car manufacturer, they have to come up with this map and they have to determine, right, that when the user, right, when the driver step on the car pedal, the acceleration pedals, right, how the engine have to respond to that acceleration pedal, that the driver step on, right? And when the engine respond to that, it have to respond in the most efficiency way, so that the driver don't need to pay high for that amount of the fuel they use when the engine check the speed. Okay, so different car manufacturer, right, then they will have this efficiency line for their own car, and this is normally represent in terms of what? The economic button in your engine console, right? Some engine or some automobiles, right, they have one button that says eco driving. If you push that button, the engine will change according to this maximum efficiency line. It will follow strictly with this line. Right? But if you don't put that eco button, right, it can run whatever. Okay, now it's on your skill of stepping down on the acceleration pedal. Okay, so any questions so far? Everybody hear me, right?
ได้ยินครับ
Okay, so this one is a typical NFC and fuel conversion efficiency, right, for different engines. Okay, so this is the number that you can use for your conventional design. As I mentioned, right, you should not go over than this number for the specific fuel consumptions, right? And this is the most that you can get if you go for conventional design, right, for different kind of engine right here. Okay, the next parameter is the volumetric efficiency. The volumetric efficiency. This parameter is used to measure the effectiveness of the engine induction process or the engine intake process. That means how good that the engine can induce the amount of air, the amount of the fuel, or the amount of the mixture into the cylinders. Okay. This parameter is only used for the 4-stroke engine, because for 4-stroke engine, you have a clearly induction process or the intake process, right? For the 4-stroke, you have one process for intake, right? But for 2-stroke engine, you don't have. It happens along with what? Compression process, right? For the intake and expansion process or the power process for the exhaust, right? So it's only used, this parameter is only used for the 4-stroke engine, right? And this parameter is defined by what? It's the actual amount of the air mass flow rate that flow into the cylinder divided by what? Divided by the physical mass of the cylinders, right? With it, what? The density of the air that come in time with the displacement volume of the cylinder, right? So density of the air time with the displacement volume, it become mass also, but this is the mass that can be occupied in the cylinders, right? Not the actual mass that flow in. The actual mass that flow in is come right here, and this is the mass that can be occupied inside your cylinder, or the maximum one. Okay, and since this is the mass flow rate here, right, so we have to time the mass down here with the engine speed. Yeah, right. Okay, and 2 come up because of what? Because it's a 4-stroke, right? We have 2 here because it's 4-stroke. That means every 2 rounds of the crankshaft, we have only 1 intake, right? We don't have every round of the crankshaft, which is represented right here by the number N here, right? We don't have every round of the crankshaft when it rotates to have intake process, right? The intake process only happen, right, every 2 rounds of our crankshaft rotation, right? So we have to come here, right? In fact, it is N divided by 2, right? But since it is N divided by 2, the 2 have to come up here. Okay. Now, If I want to make it shortly in terms of volume, right, in order to represent this volumetric right here, right, so I can change this air mass flow rate here, right, by using what? The density of the air times the volume of the air that flow in, right? And we have the same engine speed right here, right? So the volumetric efficiency will become what? 2 times the actual volume of the air that flow in divided by the displacement volume of the cylinder. Okay, so this is the definition for the volumetric efficiency. Right? And what is the typical value for the volumetric efficiency? Okay, for naturally aspirated engine, the typical value for this volumetric efficiency is 80 to 90%, right? And for the CI engine, it's higher, right? So you can expect that it's go higher than this, right? Than 90% for the CI engine. Okay, let's look at the example. Another example, we have a 3-liter. This is not one, this is L, right? 3-liter 6-cylinder SI engine operate on a 4-stroke cycle. Just a minute. Okay, we have a 3-liter 6-cylinder engine SI engine operate on a 4-stroke cycle and run at 3000 RPM. The compression ratio is 9.5. The length of the connecting rod length, the connecting rod is 16.6 centimeter, right? And the bore equal to the stroke, so it's a square engine. Right? Combustion end at 20 degrees after the top dead center. Okay, they give us that combustion end at 20 degrees after the fuel left the top dead center. The piston left the top dead center. Calculate first the cylinder bore and the stroke. Average piston speed or mean piston speed. The clearance volume of the cylinders. The distance piston had traveled from top dead center to the end of combustion. Right? That means the distance that the piston moved down from the top dead center until combustion finish, in which combustion finish at 20 degrees after the top dead center. Okay. The last one, the volume of the combustion chamber at the end of the combustion, right? If you know the distance that the piston travel from the top dead center until the combustion finish, you can determine the combustion chamber at the end of the combustion. Okay, so how we gonna solve this problem? Right? Start with the swap volume or the displacement volume of one cylinder. Right? We have 3 liter for 6 cylinder. So that means each cylinder will have about what? 3 liter, it means 3000 cc divided by 6, so it's 500 cc. Right? Change it from cc to cubic meter, so it's equal to 0.0005 cubic meter. Right? And for one cylinder, the volume can be determined from these expressions. And since our engine is a square engine, bore equal to the stroke here, right? So we can calculate for the bore of the cylinder and the stroke of our piston, right? The bore of the cylinder and the stroke of the piston in here. Then, since we know the stroke, right, we know the speed, which is 3000 RPM here. So the mean piston speed, right, it can be calculated by this. We divided by 60 because we want to show in the unit of meter per second for the mean piston speed here. Right, we know the stroke, we know the engine speed here. How about the clearance volume? We know the compression ratio, right, which is 9.5. So we can solve this equation and get the clearance volume, which is about what? 59 cubic centimeter here. Okay. And how about the crank radius? Right? Because we want to use this crank radius in order to determine the distance that the piston go. we represent by these expressions, or the distance that the piston travel. Right? So we have to come up with the crank radius. Right? We have the stroke always equal to 2 times of the crank radius. So the crank radius is equal to 4.3 centimeter. Right? Okay. The connecting rod length is given. Right? Remember, this connecting rod length and the crank radius is always constant. Right? So we have 4.3 for the crank radius, and the connecting rod length is about 16.6. Right? So when the combustion ends at 20 degrees after top dead center, the distance that our piston move is shown right here. Right? So theta is 20, the crank radius and the connecting rod length already know, right? So the distance that the piston travel when the combustion finish at 20 degrees after top dead center is equal to this, 20.71 centimeter, right? So the volume of the combustion chamber at the end of the combustion, right, then can be calculated from these expressions, right? We have VC and the volume that the distance travel, right, at the time the combustion finish, right? We know already this distance that the piston travel, so we just put it in here, and the volume is what, 70 cubic centimeters, right? So this is the problem that is very straightforward, right? The only thing you need is the definitions, right? From beginning to the end, the only tool that we use to solve this problem is definitions. Okay, definitions only. Okay. The next one is the engine specific weight and the engine specific volume, right? This parameter is considered to be important also because this parameter will indicate how good an engine designer can do in using the engine material and packaging the engine component, right? That means what material that they use for this engine, right? And how compactness the engine that they can design, right? Or in other words, how good that they can arrange all the components that required for the engine, right, within the casing or the housings of the engine, right? And that housing have to be very compact or small. Okay, so the first one is what I cannot see in the engine specific weight. Okay, the engine specific weight, right? Which is what? The engine weight divided by the rated powers, right? The engine weight divided by the rated power. The second one, the engine specific volume, which is the engine volume divided by the rated power. So that means what? If these two parameters is high, it means good or bad. If it's high, it's good or bad. If I have engine specific volume high, and if I have engine specific high, weight high, when I compare between two engines, you think the engine that have a high value of engine specific weight and high value of engine specific volume is better or worse than another engine? ตอบหน่อยได้ยินไหมฮัลโหลฮัลโหลฮัลโหลได้ยินไหม
ได้ยินครับ
ว่าไงถ้าตัวเลขสองตัวนี้สูงดีหรือไม่ดี
ดีครับผม
ดีเหรอyou think it's good that means what your engine weight is high and your rated power is low, right? If your rated power is low and your engine weight is high, then you have engine specific weight high. Same as the engine specific volume. That means your engine volume is high. That means your engine is big, right? And your rated power, that means the power delivered from that engine is low. Right? So you still think that if this two parameter is high, it's still a good engine for you? Do you think so? Still think that after my explanation?
โนครับผม
อ๋อโอเคนะถ้าสูงแสดงว่ามันไม่ดีหรอกนะแสดงว่าคุณเป็น bad engine designer แล้วนะเรื่อง material ก็หนักแถมเครื่องยนต์ก็ส่งกำลังให้คุณได้น้อยโอ้ไม่ไหวแล้วนะใช่ไหมโอเค The next one is a correction factor for power and the volumetric efficiency. The correction factor for power and volumetric efficiency. Why we need a correction factor? Because the power and the volumetric efficiency, both of them are affected by the ambient conditions. When you test run your engine, right? The ambient condition at the regions that you test your engine can affect the power and the volumetric efficiency, right? Like they said right here, right? Pressure, humidity, temperature of the ambient air all affects the mass flow rate and the power output, right? If it affects the mass flow rate, it means it affects the volumetric efficiency, right? According to the definitions, and it affects the power output of the engines, which is power here, right? So what is the typical standard ambient conditions, right? I show you here the typical standard ambient conditions, right? For the ambient conditions, we have two pressures, right? Because our air is always dry air plus water vapor, right? So we have two pressure that when we combine together, it's gonna be the total standard ambient pressure, right? Or mostly people said standard ambient pressure of the air, right? The standard ambient pressure of the air come out from two pressure. One pressure come out from the dry air, right? Which is occupy mostly of the standard ambient pressure. And another pressure is from the water vapor pressure, right? Which is smaller, much smaller, right? But if you remember in thermodynamics, we used to talk about this before, right? In the last portions of thermodynamics, when we talk about mixture, right? We have Dalton model, and in Dalton model, we said the total pressure is always equal to what? The summation of the partial pressures. Right? In here, we just don't say partial pressure because our mixture is only one, which is air, right? And our air is dry air plus water vapor, right? But in thermodynamics, mixture, when they talk about mixture, they mean so many mixtures, right? So they have to say total pressure. And the pressure of each substance in that mixture, they have to use partial pressure. But for us, we can use the name, the specific name, dry air pressure and water vapor pressure, right? In which these two are equivalent to partial pressure that we learned in thermodynamics, okay? And then the standard temperature is this, 29.4, right? So we sum these two pressure in order to get the total standard ambient pressure, and the standard temperature is only one because no matter what it is, as long as it's in the mixture and at the same region, under the same ambient condition, they always have the same temperatures. Okay, so look at how the ambient condition can affect the mass flow rate. Right? Our mass flow rate always come through the four restrictions of effect area, right? It's come from what? Nozzle, right? It come from the discharge tube in the carburetor. It come through the venturi. All of these, right, are called four restrictions of the effect area, right? Or it's come through the orifice, a small hole, right? So this is what our mass have to flow through, right? No matter it's fuel, no matter it's the air, right? And since it flow through all of this, it can be calculated from this equation. And this equation, a long one, right? This gamma is equivalent to the ratio of the specific heat, right? In which we normally use the letter K, but in here we use gamma, okay? And in this expression, you can see we have P0, we have T0 here, right? So P0 and T0 are the total or the stagnation pressure of the temperature upstream of the restrictions, right? Which is normally what? Ambient conditions, right? If we talk about the air, it's the ambient conditions, okay? But for fuel, it's different, okay? Because fuel is pumped by the pump, okay? Before it's injected through the nozzle. But if we talk about the air, it's normally ambient conditions, right? So P0 and T0 is in fact the total ambient pressures, right? And P, the letter P here, this is the pressure at the throat of the restriction, right? If it's venturi, it's gonna be a throat of that venturi. And if it's a nozzle, it's gonna be the throat of the nozzle where the air flow out. Okay, so this is the pressure at the throat. Okay, now if we assume that the pressure at the throat and the pressure divided by the total pressure or the total ambient pressure is the constant, right? When we wide open our butterfly valve or our throttle valve, right? We have no other restriction of the mass flow except at the throat of the restriction area. Right? The less we make it wide open, no restriction at all, right? So we have this P over P0 constant, okay? Because upstream already constant and at the throat become constant because we do not check anything before it flow to the throat, right? Because we keep it wide open. Nothing change over there, right? Nothing change above the throat. It's wide open. Okay, so P over P0 can be constant under this condition. And since P over P0 is constant, that means the whole term here is constant. This term is also constant, right? Okay. So the mass flow rate here now depend on what? P0 over square root T0, right? We try to keep everything the same, but still we still end up with that our mass flow rate still depend on the ambient conditions, right? And we try to keep everything as to be constant or to be the same as much as we can do. We keep the throttle valve wide open. We do not vary the position of the throttle valve, right? So we have P over P0 constant, right? But our mass flow rate still depend on the ambient conditions. Okay. How about the fuel? Okay. How about the power, not the fuel? How about the power? Now, if our fuel can consume all the air that flow in, right? So the indicated power at full throttle, that wide open, right? That indicated power will be proportional to the dry air flow rate, right? So in terms of powers, if we let all the air flow in, right, our air now depend on the ambient conditions, right? And power depend on the air and the fuel, right? So if we say that our fuel can consume all the air, right, that means the whole mixture is combusted, right? The indicated powers, right, at full throttle still proportional to the dry air flow rate. Right? So that means we can come up with these equations. Right? The indicated power at standard conditions equal to the correction factor C sub F times with the indicated power at mature conditions. Right? And this C sub F depend on the ambient condition according to this. Right? We have the pressure, right, at the standard pressure of the dry air, which is the absolute pressure here, and we have the total pressure at the measuring conditions, right, and the vapor pressures, right, the water vapor pressure at the measuring condition. Right. These two terms will give us what? The pressure of the dry air at the measuring conditions. Right. And this expression here time with the ratio of the temperature, which is the temperature at the measuring condition divided by the temperature at the standard condition to the power of 1/2 here. Right? So this is the expression for the C sub F here. Right? So if we measure the power, right, at our location, right, which is not the standard condition, it's the ambient, general ambient condition. So we will get this power. Now, if we want to convert this power to the standard conditions, we have to find C sub F here. And we can find C sub F easily from these expressions. Right? So this is how we make a corrections of the parameter that we get from the engine when we run the engine at our conditions. Right? And we can convert all this number, right, to be the number at the standard conditions by using the correction factor. Okay, and how about the brake power output at the standard conditions? Right? We talk about the indicated power at the standard condition. How about the brake power output at the standard condition? Right. So we have C sub F times PIM, right, which is the indicated power at the measuring condition. When we time with C sub F, it becomes the indicated power at standard condition minus the friction power at here measuring condition, right? We don't need to change the friction power from the measuring condition to the standard condition. We don't need to, because this is what happened inside the engine. This is what happened inside the engine, right? So no matter we put the engine to the top of the mountain, right, or at below or on the ground, this friction power is always the same, right? You don't need to change it. Okay. So that is the power. How about the volumetric efficiency, right? The volumetric efficiency, of course, by definition, it varies with the actual flow rate of the air, or the actual air flow rate, and the density of the air, right? And we all know that density varies with what? The pressure and the temperature. So that means the volumetric efficiency also varies with the ambient conditions, right? So the correction factor for the volumetric efficiency will be this one, right? It is the volumetric efficiency at the standard condition divided by the volumetric efficiency at the measuring conditions, right? Which is what? The temperature at the standard condition divided by the measuring temperature, right? To the power of 1/2. Power of 1/2 here. Okay. Okay. The next one is the specific emission and the emission index, right? Because we concern about the emissions, right? So we have to compare the emission that emits from this engine to another engine, and we use this parameter to do the comparisons, right? The emission in the engine exhaust gas are usually measured in terms of ppm or percent by volume, right? ppm, part per million, or the percentage divided by volume. Right? The specific emission can be defined related to the back power as follows. Right? So this is how we come up with the specific emission. Right? We measure the amount of the emission that come out and divided by the back power. Right? So if we measure the amount of the NOx, right? So we have a specific emission for the NOx, which is what? The mass flow rate of the NOx divided by the brake power, and so on and so forth for the specific emission for the carbon monoxide, the specific emission for the hydrocarbon. Why we have hydrocarbon come out? Because this is the unburned hydrocarbon that flow out with the exhaust gas. Right? So we have this specific hydrocarbon here also. We have also the specific emissions for the particulate or the particles, right, that come out. Right? So we have to measure the mass flow rate of the particle that come out. Right? All of this can be right in terms of what? Microgram per joule or gram per kilowatt hour. Right? You can use either one of these units. Right? So this is the specific emission. Right? The mass flow rate divided by the power output. How about the emission index? Right? The emission index is measured between what? The mass of flow rate of the emission and the mass of the fuel flow rate. Okay, so if we want to find the emission index for the NOx, then we have the mass flow rate for the NOx and divided by the mass flow rate of the fuels. Okay, other emissions are the same. Okay, for the emission index. Okay. So we learn about several parameters. Right? These sections will tell us the relationship among the parameter, the performance parameters. Right? For powers, right? We have the parameter that involve the power, such as the fuel efficiency, the fuel conversion efficiency, the fuel air ratio, right here. Right? Apart from what? The mass flow rate of the air or the mass of the air, the engine speed, the heating value, and the number of crank revolutions. Right? So in the power here, we already see two parameters that involve with the powers. Right? Now, if we go for power of the force stroke with volumetric efficiency, right, we can work out this expression to see more parameters that involve, such as, right, if we work out this equation in terms of mass here, we have the volumetric efficiency come in. We have the geometry of the engine come in, the displacement, right? Apart from the engine, the fuel conversion efficiency and the fuel air ratio here, we see the volumetric efficiency come in here. Right? For torque, right? For torque, we have fuel conversion efficiency, we have volumetric efficiency, we have engine geometry, we have fuel air ratio shown right here, and 4 parameters that involve. Okay. For mean effective pressures, right, we see 3 parameters that involve. Right, apart from the property, the density, and the heating value. Right. For specific power, which is the power per unit piston area. Right. This specific power is the power per unit piston area. Right. You see the same 3 parameter, performance parameter, which is what? Engine conversion efficiency, the spec and volumetric efficiency, the fuel air ratio shown right here. Right. In which, if you want to see more, right, you have to work out these equations, right, and then another parameter that you see is the mean specific, mean piston speed here, right, apart from the 3 parameters that we just mentioned. Okay, and then if you want to squeeze this expression into the short form, right, you will see that this specific power, right, depend on 2 performance parameter, which is the mean effective pressure and the mean piston speed shown right here. Right? So this show you the relationship among the performance parameters. Okay. So in conclusions, good engine performance depend on what? Depend on high fuel conversion efficiency, right? If you look at this, of this here, right? If you have high fuel conversion efficiency, you have a good engine performance. High volumetric efficiency, right? The maximum fuel air ratio that can be burned in the engine, F over A, right? F over A. How much that you can supply the mixture at this maximum ratio. Okay. High mean piston speed. Okay. All of this will give you a good engine performance, right? And now, if you want to increase the output for the given displacement engine, right, you can do by increasing the inlet air density, right? Now, if you go back and look at the property, you want to increase this power, right? That means you have to increase this density, right? The density of the air, because it involves in terms of power, involved in the mean effective pressure and so on, right? So you have to increase the inlet air density. How we can increase the inlet air density? Right? By using turbochargers. Right? Okay. So that is the conclusion for the good engine performance, right? After we know the performance parameter. Right? So this is the development of our design. Right? Apart from being able to design the engine, we have to know how we can develop our design in order that our engine can have a better and better performance. Okay. The last one is the engine design and performance data. Right? That means after we doing our designs, right, we have to build it. Right? And after we build it, then we have to test the engine, right? And by testing the engine, we collect the performance data, right? So you see the step of the story that we give you a lecture, right? Engine design, develop the engine design, and then finish our design by making the engines. And after we make the engines, we have to test run the engine and then collect the data, right? So for comparative analysis between different engines, right? One people design one engine, another design another engine, and we want to do the comparisons, right? We have to make several significant measurements, right? In order to come up with the data, right? And these significant measurements have to be done at various engine operating points, right? That means have to be done at many running conditions of the engine, such as what? You run the engine at the maximum or normal rated point, right? Or run the engine at maximum or normal rated condition, right? At this condition, what do we measure? We will measure the mean piston speed, right? Why? We want to compare the success of each engine in handling the load that due to the inertia of the part, right? Because piston moving considered to be the inertia, right? So we want to look at when the engine run at maximum or normal rated condition, right? What is the mean piston speed that it can keep us? Okay, because this will indicate how good it can handling the load that happen because of the inertia of the part, right? Apart from this, right, we want to see how good that it can encounter with the resistance to the airflow and or to the engine friction, because the piston move within the cylinders, right? And again, what? The pressure that from the air that flow in. Okay. We also measure the power per unit piston at this condition, because we want to look at the effective use of the piston area, right? the piston that we design with this frontal area or the top surface area of the piston, how much the power that can be delivered or come out from this area of the piston, right? Regardless of the engine cylinder size. Okay, cylinder size means the volume of the cylinder, right? Different volume of the cylinder, we can have the same bore of the cylinder. That means the same piston diameters. Okay. We measure also the BMEP, right? Because we want to see that if we design for naturally aspirated engine, we want to look at the ability of this engine to intake the air, which represent in terms of the volumetric efficiency. We want to look at the effectiveness of the air utilization in the combustion, which we look at the fuel air ratio that this engine can receive. Okay, and also for I cannot see this. We have, please move this window away from the share application. Anyone see also the same? Okay, it disappear now. Okay, if we design for the supercharged engines, right, we want to look at the success, right, for this engine in handling higher gas pressures and also the thermal loading that happen because of that. Okay, so for naturally aspirated, we want to see, we can look at the volumetric efficiency, we can look at the fuel air ratio, right? And then for the supercharged, right, that means now we have higher gas pressures, right? So we want to look at the engine can handle this higher gas pressure or not, right? And also the thermal loading that result from that. Right? We look at the specific weight, right, to see how effectively that the designer of that engine can use the material for the engine. We also look at the specific volume, right, to see how good that they can use the engine space, right, to put in all the components of the engine into the housings. Okay. We also run the engine at all engine speed with throttle widely open or maximum fuel pumping setting. That means we deliver the maximum amount of fuel to that engine with fully open of our throttle and run at all available engine speed. Right? At this condition of running the engine, we will measure the BMEP. Right? We measure this BMEP so that we can know the ability to obtain or provide the high airflow and effective use of the air over this full length of the engine speed, right? Because BMEP will tell us that how this engine, right, can obtain or provide the high amount of the airflow under wide open throttle, right, and effectively use of air over the full length because of the maximum fuel pumping setting. Okay. We also run this engine at the useful regime of the engine operations, especially for a long period of time, right? Now, this running, we will run the engine at a long period of time or several hours, right? Under this condition, with a long range of time in running the engine, right? Other condition, you might not need to run the engine for a very long time, right? You run the engine so that you get the data that you want and then you change the condition. But for the last one, you will run this engine at one certain condition and run it in a long time, right? For this, you want to see what? You want to see the brake specific fuel consumption or the fuel conversion efficiency. That how much this engine, if it runs in a longer hour, how much you have to pay the money. And also the brake specific emissions, right? Because you run the engine in a long time, you want to see how much of the emission that this engine will emit from its running. Okay. Okay, so that the end of the lecture number 2. Any questions? Any questions? Any questions? มีคำถามอะไรไหมครับ
ไม่มีครับผม
ไม่มีเคลียร์นะทุกอย่างเคลียร์ Okay, good. Maybe we stop for 5 minutes or 10 minutes, and then we come back with the last lecture in this series. Okay, 10-minute break, or you want to go for keep going?
เบรกก็ดีครับผม
Break นะ Okay, so 10-minute break. We will come back at 10:45. Okay, about 10:45. Okay, so break 10 minutes. Okay, everybody come back. Everybody come back ready. Hello. Hello. 24 student นะ Okay.
ครับ
Come back กลับมาแล้วนะโอเคนะ so everybody ready for the second round of our lectures นะ we finished the first round already the second round okay so these lectures will be about the inductions and the exhaust right because we used to talk about the scavenging process or the gas exchange process, right? That happen in both for the 4-stroke, for 2-stroke, for benzene which is SI engine, and for the diesel which is CI engine, right? The scavenging process or the exchange process, right, play a very important role, especially for the 2-stroke engine, right, in which we don't have a distinct intake process or the distinguished exhaust process or a clearly intake or the exhaust process, right? Not like in full stroke that we have clearly the one intake stroke and one exhaust stroke, right? I mean, the whole stroke occupied by intake and another stroke occupied by the exhaust. But for 2-stroke engine, we don't have things like this happen. Right? So scavenging process or the exchange process play an important role on that 2-stroke engine. Okay, so induction and the exhaust process or the gas exchange process take an important role to the performance and efficiency of the engines. Okay, for the 4-stroke engine, these two processes controlled by what? Valve, right? We use the valve to open and close, right? When we open the inlet valve, the intake process happen. When we open the exhaust valve, the exhaust process or the exhaust stroke happen. Okay. For the 2-stroke engine, right, the flow of the inductions and the exhaust gas, the intake and the exhaust gas, this flow is regulated by the piston covering and uncovering port, right? Because we use the motion of the piston when it move up and down, to open and close the port. Okay, so in terms of using valve, right, we have 4 types of valve that we can use for the 4-stroke engine. Right, we can use the puppet valve, we can use the sleeve valve, we can use the rotary valve, and we can also use the disc valve. Yeah. ไม่ไปอีกแล้ว งงจริงๆงงมากมีเข้ามีออกปุ๊บมันจะต้องสไลด์ไม่ได้โอเค Okay, so this is what we call the puppet valve, right? The most commonly used valve that you see in most of the car manufacturers. Sometimes we call it a mushroom valve because it look like a mushroom. The shape look like a mushroom, right? Okay. The reason why we mostly use this valve or commonly used valve because this valve is cheap, right? When you manufacture this shape of the valve, it's not so complicated, so that make it cheap. Apart from this, not only it's cheap, it also have a good flow property, right? Because due to this shape of the valve, the air or the fuel mixtures or the mixture can flow without much resistance due to that flow. Right? It also have a good seating, right? Because of this mushroom shape, right? So a good seating is important for sealing the opening, right? Because this valve is used to open and close, right? So when you want to close it, you want to make sure that it's closed tightly, right? The seal have to happen, a good seal have to happen. So with this shape of the valve, right? The front shape of the valve that look like this, you can have a good seating of this valve, right? It's easy to lubricate because the shape is not complicated. Very straightforward, very simple shape. And by that, it also have a good heat transfer to the cylinder head, right? Because it can transfer the heat that inside the cylinder and to the cylinder head where this valve is located. This is the rotary or abyss valve, right? They are rarely used or sometimes used, right? But this valve is not commonly used because they have problem about the heat transfer. They have also the problem about the lubrication and the clearance, right? In which you can see, right? These two valves rotate. Right? So the clearance to manufacturing this valve, right? In order for this valve to have a good clearance, it's very difficult, right? And because of the shape which is round, right? They don't have much heat transfer area when the heat happens, right? And also because of the round shape, right? They have the problem about the lubrication. The same as the disc valve shown here, right? They have a rotating port here, right? This one will rotate here. So every time that it rotates to match with the opening here, the valve open. But every time that it rotates with the closed portion of on the top part, right, the valve is closed. Right? Have the same problem, heat transfer, lubrication, and the clearance. Okay. This is the sleep valve. This sleep valve, they said, is best suited for the aerospace engine. Right? What they mean aerospace engine is the old aerospace engine. In the past, we use the reciprocating engine as the aerospace engine. Not like today that we use the gas turbine or the jet engine. Okay. So this is how the sleep valve works. Right? You have the sleep valve here that go along with the piston. Right? They move in the linear motion with the piston, right, in order to open and close the port here. Right? Close the port here. Also here, the port exhaust and the intake down here. Right? The advantage for this sleep valve is that it helps eliminating the hot spot, right, that come with when we use the poppet valve, right? Because the poppet valve have the face look like this, right? The surface area is not that much, so it have a chance to create some hot spot on that surface area. But for the sleep valve, right, the surface area is higher, right? So there is no hot spot that come up with the sleep valve here, right? This sleep valve is also good because it can produce the higher output and higher efficiency, because when you use this sleep valve, you don't need to concern about opening and close on the top. That means you can go for a higher compression ratio, right? Because if you use the poppet valve, the opening and the close is on the top, but this one is on the side, right? So you can do the, you can have a higher compression ratio, right, within the cylinder. Okay, without afraid that anything will leak out. Okay. The disadvantage for this sleep valve is that the cost to manufacture and the difficulty to manufacture. Right. This is the problem that come up with the sleep valve. It also have a lubrication problem, right? And also the friction problem that happen between the cylinder wall and the sleep valve, right? Because it move along with the piston, right? Both of these move along the cylinder within the fixed portion, the red color here, right? So result in what? Lubrication problem, higher surface, you need higher lubrications, right? And also because of higher surface, right? Friction is the surface phenomena. So if you have higher surface, you have higher problem on the frictions. Right? You also have heat transfer from the piston to the sleeve and the oil film to the cylinder because of the higher surface. Right? Heat transfer and friction are all surface phenomena. So if you have higher surface area, right, that means this sleeve valve can transfer the heat that happen inside here to the cylinder wall. Okay. So you have this advantage for the sleeve valve. Okay. Let's look at the valve mechanism. We used to talk about this before, right, in the lecture 1, right? We repeat it again here. A camshaft is an important portion in valve mechanism because this camshaft is used to operate the valve. When we talk about operate the valve, we talk about opening and closing, right? So for the overhead poppet valve, right, camshaft can be either mounted in the cylinder box, so like this, right, not on the cylinder head. It can be mounted in the cylinder box or in the cylinder head like this, right? Both of these are called overhead poppet valve because the valve is on the top here, right? No matter that the camshaft is on the side or on the top. Okay, if it's on the side, it's mounted in the cylinder box, not on the cylinder head, right? And this is mounted in the cylinder head. Okay. And this camshaft is driven by what? By chain or by the tooth belt, right? We see that before, the timing belt, right? This one is by the chain. Okay, most of the European car, I believe they use the chain. Right? The reason why the Japanese car, they don't use chain because they say it's noisy. Right? If you use chain, it creates noise. So mostly they use time belt, but nowadays they gradually switch from the timing belt to the chain because if you use the timing belt, then I believe about 100 kilometer or 150 kilometer, you have to change the belt. Because if the belt broken, that's the major problem. Because your valve will open and close like a lock. Right? It's go up and down because no more people to control the timing of the valve because the timing belt is broken. Right? So you have to go for a major overhaul if that problem happens. But for chain, you can use it forever. Right? It's never broken. Right? You can use it forever, on and on and on. Right? So the major overhaul because of the broken belts, right, to the engine, right, will never happen. Okay. You can also use the clear die like this. Seldom see it, right, by using the clear die, right, to drive the crankshaft. Okay. Okay. Presently, right, most of the car manufacturers use twin or the double overhead camshafts. Right, that means they have two intake and two exhaust valve per one combustion chamber or per one cylinders. Right, and they have two overhead camshaft because one camshaft will operate the inlet valve and the other camshaft will operate the exhaust. Right, like show like this. Right, we have two camshaft here. This is the overhead camshaft. One operate all the intake, another one operate all the exhaust. Okay. And this is the animation when these two camshaft operating. Okay. Okay. People also come up with like 4 valve operations. That means 2 intake valve and 2 exhaust valve by using one single camshaft. But no need to use 2 camshaft. The reason is because they want to reduce the inertia that happen due to more part installed in the engine, right? With 2 camshaft, you have 2 more inertia, right? So some designers, right, such as this one, Business Leyland, right? He designed a single camshaft, right, that used for 4 valve operations, right? And this is the picture of this mechanism. Right? They have only one single camshaft here, right, that can operate 2 valves, right, by using the locker arm here. Using this locker arm here, right? So the camshaft will come in direct contact with the inlet valve here, right? When this camshaft rotates, and along the way that this camshaft rotates is also have direct contact with the locker arm here. So this locker arm will swing up and down, right? Every time that this camshaft rotates, and by this swing motion, right, it will force this exhaust valve to open and close. Okay, so one single camshaft operates two valves by using these mechanisms, right? Yeah. So instead of having a long camshaft, another one camshaft, right? Now they have a short locker arm here. So it helps reducing the inertia that happens because of the roller mass. Okay. Now, why they use 4 valves per combustion? Right? People before that they have 2 valves per combustion chamber, but nowadays I would say 100% of the car here they have 4 valves per combustion chamber. Some even have 6 valves or 8 valves per combustion chambers. Right? So what is the advantage of having more valves per combustion chamber? Right? It results in what? For the larger valve throat area. This is what happens if you have 4 valves per combustion chamber. You have a larger valve throat area for gas to flow, right? No matter it flow in or flow out, right? Because you have larger valve throat area here, right? Apart from this, since you have more valve, right? Each valve will be smaller, right? For the same amount of the airflow because you have more valve, right? And this more valve, that means you have valve smaller, and when valve smaller, right, you require a smaller valve force to open and close the valve, right? And apart from this, you can also have a larger valve seat area, right? Now, larger valve seat area, so when you go for manufacturing, it's easy to manufacture, okay? The reason for having small valve force is because a lighter valve with a lighter spring will reduce the hammering effect on the valve seat. This is also another advantage apart from lower inertia, right? Because of small valve force, right? When this valve force react to the valve, right? Instead of making a loud noise, it makes just a very small noise, right? The hammering effects small. You hardly hear the noise of the valve when it open and close, or when it sit or not sit on the valve seat. Okay, this show you the camshaft configurations, which is the double overhead camshaft with the direct acting valve. I want to show you this because before that I show you the locker arm, right, in the valve mechanisms, but now today this is the configuration that they use, right? No more locker arm, right? They have a direct contact, right? That means the cam direct contact with the valve tip, right? No need for the locker arm to make that contact, right? So all the development that you see, right, go to reducing of the inertia that happen. That means your engine can come up with higher power because of the inertia that reduce. Okay, so it show you here. Okay, the cam here. I show here the locker arm, small one here, right? Attached to the valve tip and with the automatic valve adjuster, right? To make sure that they always have a close contact with each other every time that this mechanism works. Okay, this automatic valve adjuster make sure that the contact, a close contact happen. Okay, no matter how long you use this engine. Okay, and this is I show you the configurations of the valve mechanism. This is called the inverted bucket. This portion inverted bucket, right? You have a cam here. Okay, This is called the overhead camshaft with direct acting inverted bucket follower. Okay, so instead of having direct contact here, they have an inverted bucket here. This is a side camshaft with the push rod and the locker arm. Right? You have the push rod here on the side. You have a locker arm here, right, that make contact with the valve here, and the camshaft is down here. You have an overhead camshaft with direct acting and pivot locker arm. That means you have a camshaft here, right, that make contact with the locker arm that is pivot. The end pivot is right here, right. So the locker arm go up and down to open and close the valve here. Okay, so that is the many valve mechanisms. Okay. The next one is the valve timing, because the valve have to open and close, right? So we need the timing for the valve to open and close, right? This valve timing is characterized by the camshaft and the valve mechanism. That means with camshaft and the valve mechanism, right, itself can help the valve to open and close properly. That means provide a good timing for the valve to work. Right? And when valve is working, right? When valve is working, sometimes we will see the valve overlap that happen. What is the valve overlap? Right? The valve overlap is the period when both the intake valve and the exhaust valve are open. Right? So that's shown right here. Right? It's a two round of the circles. Okay, the first round is this, right? And then you have a second round here. Okay, so when you see this, right, the blue color represent when the intake valve open. The red color represent when the exhaust valve open, right? And in this picture here, you see the area where the red and the blue are overlap with each other, right? That means what? That means this area here represent that both intake and the exhaust valve open, and this happened twice, right? Not only once, it happened twice, 2 times during the cycle of the engines. Okay, so there are 2 overlap timing process. One is short, one is big, right? How big is it and how short it is depend on what kind of the engines that you want it to be. Okay, if you go for small valve overlap, for this 2 overlap timing process, right? Let's say 15%, 15 degree of the crank angles, right? This is usually for the compressed ignition engine and for the conventional SI engine, right? That means they use a small overlap timing here, right? And that amount is about 15 degree of the crank angles. For large overlap here, right, go up to 65 degree of the crank angle. This is for the engine that you expect to have a very high performance. That means you have to have a large overlap if you design engine to have a high performance one. Okay, from the circle, right, we can make a plot on the valve timing like this, right, by representing through the valve lip, right, or the lip of the valve, right, when it's closed and open, right, and the crank angle position here, right. You also see the overlap region right here, right, where the exhaust valve still open and the intake valve still open, right. So you can see the valve overlap either through this valve timing diagram or this diagram, right, which is the valve displacement diagram here. Right. The opening of the exhaust gas along with the crank positions, the opening and closing of the intake valve along with the crank positions, and you see the overlap here. This overlap can be either 15 or 65, depend on what kind of engine you want to be. Okay. Now, for the small overlap, okay, for small overlap, what happened? Right? If you go for the small overlap, small valve overlap, right, you can have the pressure inside the cylinder build up rapidly, right? Because the time that both intake valve and the exhaust valve open together is short, right? So most of the time, your cylinder is a closed vessel. So by that, the pressure inside the cylinder can be built up rapidly. Okay. Another thing that you want to happen, right? If you go for the small valve overlap, right? Or another thing that you can get if you go for the small valve overlap is that you will have less air fuel mixture that can be pushed out by the piston face because of the small overlap of the intake valve and the exhaust valve, right? When it open together, you can expect that when the intake open, you have mixture flow in, right? And when the exhaust flow out, you have exhaust flow out, right? And if both open together, right, you can expect that some of the mixture that flow in, some portion of this can go out, right? So if this opening is short, right, so less air fuel mixture will go out by the piston face. But this is also have a good point, right? Because you have more fuel air mixture in the cylinder. So if you start the engine in the cold weather, you will have less difficulty for the cold start. Right? This is especially good for the CI engine which have no spark plug to help them to ignite. Right? But for SI engine, we have the spark plug, right, to do the ignitions. But for CI engine, it depends totally on itself, right? If it under the cold weather, right, that cold weather will affect the starting of the CI engine. Right? So you can help them a little bit by having more fuel air mixture in the cylinder when it flow in because of small valve overlap here. Okay. Apart from this, right, you have more time for the product of combustion to leave the chamber. Right? That means you have small opening between these two. That means you have higher time for the exhaust valve to open. Right? So more time for the exhaust valve to fully open here. Right? That means you have more product of combustion or the exhaust to go out. Okay. How about for large valve overlap? Right? If you have a large valve overlap here, what happens is you will have some unburned fuel that will cross flow from the inlet manifold into the exhaust valve, right? Because your intake valve open while the exhaust valve also open, right? So your fuel air mixture come in, right? Since the exhaust valve still open, so there is a chance that the unburned fuel, which is the air fuel mixture, will cross flow, that means flow across from the inlet manifold to the exhaust valve. And that means the efficiency of your engine will be reduced. Okay. With large valve overlap, right, you have a chance to increase the level of residue in the combustion chambers. Right. This increase on the level of the residue, right, will create the significant effects on the combustion process. Right. The residue is something that left over in the combustion chamber. It do not flow out. Right. If it have a high level of this residue, it gonna affect the combustion process, and that means the efficiency also decrease. Okay. So with large valve overlap, right, the only performance that you expect to have to be affected is the efficiency. Okay. So this is the only one performance that gonna be affected by the large valve overlap. Okay. So you might not confuse. I talk about this because you will not confuse about this. Because in the previous slide we said large valve overlap. This is for high performance SI engines, right? and people might think high performance. So in here, efficiency reduced. Wow, so how can it be high performance? When we talk about the high performance of the engine, we not only talk about efficiency, we talk about some other parameter as well, right? In here, they just only talk that if you have a large valve overlap, what parameter gonna be affected by the large valve overlap, right? Other parameter get a good benefit from the large valve overlap so that you can have a high performance SI engine on them. Okay. Okay. How about the level of the residual, right? The level of the residual increase with what? Decreasing of the absolute inlet manifold pressures, right? Because of large valve overlap here, right? So you have the decreasing of the absolute pressure there. Reducing of the compression ratio, right? This happened also for the large valve overlap here. Increasing of the valve overlap already direct. Okay. Decreasing of the speed. Okay. If you have large valve overlap, that already affects the level of the residue, and your engine speed is reduced, this even more affects on the level of the residue. Increasing of the exhaust back pressure, because more time, right, for the exhaust valve to open together with the intake. So the pressure outside, this is called the back pressure, can be affects the what happened inside the cylinder, right? So the residue can hardly flow out because of that back pressures. Okay. Okay. So to perform the valve timings, right? We normally represent by the valve timing diagram. You see the previous one is not a tiny one, right? Because the main purpose is only for you to see the overlap that happened, right? For a complete time of valve timing diagram, it has to be like this, in which you see two complete rounds of the circles. Start from here. This is the first round, end up here. Oh, okay. From here. Okay. Yes, and here. And then the second one from here and here. Okay. So this is two complete round here, right? So what are the information that you will get when we draw a valve timing diagram? Okay. Start from the inlet valve here, right? The inlet valve open here, right? From the valve timing diagram, we can see that the inlet valve open 20 degrees before the top dead center. This is the top dead center here, right? And then it keep opening, so the suction or the intake happen until it's closed here, right? In which from the valve timing diagram, we can see that the inlet valve closed at 35 degrees after the bottom dead center, right? So this is the distance or the time, right, that the inlet valve open. Okay, the inlet valve open here, and the distance that the piston travel, okay, from here to here, right, until the inlet valve close, right? So you can see that we have more time for the fresh air to go in, or the air fuel mixture to go in, because we want to take the advantage of the momentum from the rapidly moving gases, right? Because gas is keep moving, so it have momentum happen. So we make use of that momentum to induce more of the gas to flow in. Okay, and then after the inlet valve close, compression happen, right? And ignition take place here, right? From the valve timing diagram, it says that the ignition occur at 35 degrees before the top dead center, right? So we have ignition early, right? In order for what? To allow for the time delay between the spark and the commencement of combustion, right? Because we know that ignition happen doesn't mean combustion also happen. Combustion needs time, right? So ignition happen first and combustion take time to open to occurs, right? And the most preferable position for the combustion to take place is at the top dead center, right? But seldom that we have it at the top dead center, right? We normally have it before because we want the combustion to happen before here. Why? Why? Because we want the pressure to have time so that the pressure inside the combustion chamber or the cylinder can reach the maximum pressure when it at the top dead center. This is the key point. This is the key point, right? If we have the combustion happen at the top dead center, the maximum pressure will happen after, right? So we ignite first and we expect that the combustion happen along the way here, right? So that the pressure that come up due to combustions have time before it reaches the maximum, right? And we hope that it reaches the maximum at the top dead center. This is the ideal position for the maximum pressure to happen. But unfortunately, we rarely have this happen. We normally have the maximum pressure happen after the top dead center. If you remember the event that I show you. Okay, so ignition happen here, and then after that combustion, and then expansions, right? And from the valve timing diagram, you see that the inlet valve open here with it 35 degrees before the top dead centers, right? Because we let this inlet valve open because we know that they have a high pressure from here, right? Start from here, you have high pressure, and the piston move down, try to reduce this pressure to convert this pressure into work, right? But even this piston moving down, it may not rapid enough or fast enough to reduce this enormous pressure, right? So the exhaust valve open early, right? So that we can reduce the size or the magnitude of the pressures, right? Okay, and the work, we also need the work to expel the gas, right? Because in here we still have high pressure above the atmospheric pressures, right? So we make use of this pressure to expel or discharge the exhaust gas out from the cylinder by letting the exhaust valve open first. Okay, so the exhaust valve open at 35 degrees before the top dead center, and then when the exhaust valve open, that means the exhaust process happen and it finished here. The exhaust valve closed at 10 degrees after the top dead center. So along the way here, from the inlet valve open here to the exhaust valve closed here, this is the overlap period, right? And from the inlet valve, the exhaust valve open here until the inlet valve closed, this is another overlap period, right? Okay. So these are all the informations on the valve timing diagram, right? That we know when the valve is open, when each valve is open, when each valve is closed. Okay, when ignition happens. Okay. The last one about the valve calculations, small valve calculations. Okay, this is the picture of the valve that we use for our calculations. We have the vertical distance here when the valve open, right? Represented by the letter L here. This is called the valve lip. This is called the valve lip, right? And the amount of this valve lip is generally on the order of a few millimeter to more than a centimeter, right? So it starts from, let's say, 5 to 10 millimeter. This is a few millimeter to a little bit more than 25 millimeter, which is 1 centimeter, right? And the maximum lip or the maximum of the valve lip is always less than the diameter of the valve divided by 4. Right? So this is the maximum distance that the valve can be lifted. Right? Always less than the diameter of the valve divided by 4. Okay. How about the average velocity? The average velocity, right, through the intake valve or the port. This is the average velocity of the mixture that flow through the intake valve or the intake port. Right? It can be calculated from what? The average velocity of the valve the average velocity through the valve times the valve or the port area. Right? If we make move this one to this side, it will be equal to the piston speed times the piston area. Right? The speed or the velocity times the area represent what? Represent the volume flow rate, right? So the volume flow rate that flow in equal to the volume flow rate that receive, right? This equation tells us this. Right? The volume flow rate that flow in, which is the average velocity through the intake valve times the valve or the port area or the area of the valve. Right? This is the volume flow rate that flow in equal to the piston speed times the piston area, which is the volume flow rate that receive. Right? They are the same. So we make use of this to come up with the average velocity through the intake valve by knowing the piston speed here, the piston area here, and the valve area here. Okay. Since this is the flow through the openings, right? We have a resistance. Right? So this resistance will tell us that the actual flow rate will not equal to the theoretical one, right? So we have the ratio of the actual flow rate area to the flow passage area, in which we call it the valve discharge coefficient, the valve discharge coefficient, right? CDV. Right? So we have the actual flow area, in which this is the actual flow area, right? Smaller than the physical flow area that we have here. Right? This is the physical one. We have this much, but the actual is like this. Right? The physical one we call it the flow passage area here. Right? The ratio between these two we call is the valve discharge coefficient. Right? Where CDV is greater in low valve lip than the high valve lip. Right? That means for lower valve lip, these two areas are approximately or nearly the same. That's what they say, right? If this valve lip is small, these two areas are nearly the same. So our CDV is greater in that. Okay. Okay. The flow passage area, which show right here, can be calculated from this expression. Is equal to pi dV, the diameter of the valve, times width the valve lip. Right. So this is the physical area of the flow or the flow passage area. Okay. The minimum valve intake area, here, right, which is an actual one, depend on what? Depend on the mean piston speed, right, or depend on the diameter of the valve. This is the minimum valve intake area here, AI, right, pi over 4 dV to the power 2, or it's equal to 1.3 times the bore of the cylinder times with the maximum mean piston speed divided by what? C sub I, the speed of sound at the inlet conditions. Yeah. Right. So this is the minimum valve intake area that required, right? Based on the maximum mean piston speed here and based on the diameter of the valve. And this expression here usually represents the total inlet valve area for one cylinder, no matter how many valves you have, right? How many intake valves you have in that cylinder. Right? So this is the total one. If you have one intake valve for this one cylinder, right, this is the intake valve area for that valve, which represent the diameter of that valve, right? But if you have 2 or 3 intake valve, that means if you want to find the diameter of each valve, you have to divide the results from this by 2 or 3. Right? Then you will get the diameter for each valve. Okay, so you have to clearly understand that this expression is the total intake valve area or the inlet valve area. Okay, so examples, right, to do for the valve calculations. Right? We have a 2.8 liter 4-cylinder square engine bore equal to the stroke, right? With 2 intake valve per cylinder, not just 1 intake valve per cylinder. Right? It is designed to have a maximum speed. Right? This engine is designed to have a maximum speed of 7,500 RPM. Right? The maximum one. The intake temperature is 60 degrees Celsius. Calculate the intake valve area, the diameter of the intake valve, and the maximum valve length. Right? So in order to calculate all of these 3, right, we know the bore, we know bore equal to the stroke, we know the displacement, right? So we have to make use of these expressions. Okay, first we calculate the sound, the speed of sound first. We know the temperature, right, which is 60 degrees Celsius. We know the R, the constant value, right, of the air. We know the gamma, right, Cp over Cv, right? So with this, I can calculate the speed of the sound, which is 366 meters per second, right? And then the displacement volume for each cylinder, we have 4 cylinder, 2.8 liter. So the displacement volume for each cylinder is 0.0007 cubic meter, right? And then for the bore equal to the stroke, I can calculate the stroke and the bore from the displacement volume of 1 cylinder. And with this, I can further calculate the mean piston speed here, right? And this is the maximum one because the maximum speed already know, right? So the maximum mean piston speed is 24.1 meters per second, right? And since I know the maximum mean piston speed, I know the speed of sound, I know the bore, I can calculate the total intake valve area for 1 cylinder, right? So this is the total intake valve area, 7.92, right, square centimeter. Now, and we have 2 intake valve per cylinder, right? So each intake valve area for each valve, the intake valve area for each valve will be the total divided by 2, right? And with this, I can come up with the diameter of each valve, which is what? It's equal to 2.25 centimeter. Right? This is the diameter of each intake valve in this cylinder. Right? And the maximum valve lip will be what? The diameter divided by 4, right, equal to 5.6 millimeter. Okay. So this is the example of valve calculations. Yeah. Okay, so we finished before time. Huh? Any questions on the last lectures about the gas exchange process and about the valve timing diagram? Okay. Any questions on that?
ไม่มีครับ
No? Okay, good. Okay. So if no questions, we will finish our lecture for today. Okay. If no question, any question about the homework? No? No?
ไม่มีครับอาจารย์
ไม่มีนะ โอ้โห ดีมากเนี่ย ไม่มีหมดเลย อธิบายไปเข้าใจหมด เยี่ยม ใช้ได้นะครับ โอเค so see you next week. Okay. See you next week. Bye bye.
สวัสดีครั
สวัสดี
บ
ครับ